Welcome to Science Views from the Valley. I'm your host, Dr. Kelly Kassan. Science Views from the Valley is a monthly program that will explore interesting science topics and how they relate to the San Luis Valley and the Upper Rio Grande region. I received a request last month to talk about Mars and what we have learned from the different unmanned missions that have been sent there. Though it may seem strange that a biologist would talk about astronomy, I was originally an astronomy major in college and did an internship at Lowell Observatory in Flagstaff, Arizona. In fact, I will be discussing Percival Lowell, the founder of Lowell Observatory, a little later in this broadcast. Mars has always been a fascination to me. I am an amateur astronomer to this day, and I'm excited by the prospect of astrobiology, the possibility of life outside of planet Earth. Mars, being similar to Earth, is considered to be one of the most likely candidates to have life. Mars is the fourth planet from the Sun, though the second smallest planet. Only Mercury is smaller. Mars lies between Earth and the asteroid belt, a ring of irregularly shaped rocky objects too small to be considered planets. Mars is called the red planet because even if you look at it in the sky, it has a slightly reddish hue. This reddish color is caused by the abundance of iron oxide, in other words, rust, on the planet's surface. So Mars is not only the red planet, it is also the rusty planet. Though Mars is considerably smaller than Earth, approximately 1/2 the size, it has a similar rotation as Earth. Planet rotation determines the day length. Mars has a slightly longer solar day than Earth, a little less than 25 hours compared to 24 hours Earth time. The axial tilt of Mars is also similar to Earth's, meaning that Mars experiences spring, summer, autumn, and winter, much like Earth. The Martian year, however, is nearly twice as long as Earth's year. A year is the amount of time for a planet to complete an orbit around the Sun. Mars is further from the Sun than Earth, thus it has a longer year. Earth's atmosphere consists of 78% nitrogen, 21% oxygen, 0.9% argon, and trace amounts of carbon dioxide, methane, water vapor, and neon. The Martian atmosphere, however, is quite different. From the data we have collected so far, the Martian atmosphere contains 95% carbon dioxide, 3% nitrogen, 1.6% argon, which is an inert gas, and a trace amount of oxygen, carbon monoxide, water, methane, and a lot of dust. The dust is why the sky is so colorful in the photos that have been sent back from various landers and probes we have sent in the past few decades. Unlike Earth, the Martian atmosphere has a very weak ozone layer that varies greatly depending on the location and time. This means that UV light from the Sun would reach the Martian surface unhindered and unfiltered, which is detrimental to any organic compounds that may be on the surface. UV light also increases the breakdown rate of organic molecules. The lack of ozone is considered to be the reason why so few organic molecules were found by the Viking landers in 1970s. The temperature on Mars is also considerably colder than the Earth's. The average surface temperature on Earth is 58.62 degrees Fahrenheit. On Mars, the average surface temperature is a balmy -81 degrees Fahrenheit, which rivals the temperatures we see in Antarctica. So we have several problems with finding life as we know it on Mars. The atmosphere is low in oxygen, it's very thin, does not filter out damaging UV light, and the surface temperature is much lower on average than the Earth's surface temperature. So even plants, which would thrive in a high carbon dioxide atmosphere, would have a lot of problems surviving the damaging radiation and far below freezing temperatures. So, does this mean that life as we know it could not be found on Mars? First, let's talk about the needs of life as we know it here on Earth. All living organisms on Earth requires organic, in other words, carbon-based molecules, energy, and water. Living organisms are carbon-based and use DNA as the genetic material. Some people have suggested that silicon life forms, life based on silicon compounds rather than carbon compounds, might exist under certain conditions. Indeed, the episode Devil in the Dark from the original Star Trek series featured a silicon-based life form. But silicon-based life forms are unlikely to exist on Earth-type planets for several reasons. The element silicon lacks the ability to form long molecules that would carry biological information, unlike the long DNA polymers seen in carbon-based life forms. Unlike carbon, silicon does not interact with many other types of elements, reducing its ability to form diverse molecules seen in carbon-based life forms. Finally, silicon molecules are highly reactive with water, so a different solvent, like acetone or alcohols, would be needed in silicon-based life forms, yet these solvents are also highly flammable. Under certain environmental conditions, maybe silicon-based life is possible. It's not impossible. But silicon life forms would be unlikely for an Earth-like planet like Mars. Water is also important to life as we know it. We do know that water once flowed on Mars. We see the remains of channels, valleys, and dry lake beds that were carved by abundant water in Mars' past. Today, however, the only water visible on the surface is at the polar ice caps and a few other regions on Mars. Certainly some species could adapt to using water that is locked in the ice or soil. Some species on Earth, like the tardigrades, are known to go into a type of dormancy, surviving up to 30 years without water due to protective proteins that prevent structure damage during this period of desiccation. Though most life prefers warmer temperatures, most of Earth's biodiversity is at the equator, quite a few species have adapted to much colder temperatures. Polar bears, yaks, penguins, and seals are examples of animals that have not only adapted to cold temperatures, but would have difficulty surviving in much warmer climates. Conifers, willows, moss, lichens are examples of plants that have adapted to living in freezing temperatures. Extremophiles, organisms like archaea, are also able to live in extreme, harsh environments. Thermophilic archaea and bacteria live in the geysers in Yellowstone National Park, where the water temperatures can be above the boiling point of water. A bacterial species, Deinococcus radiodurans, is known to survive cold, dehydration, vacuum, and acids. This species can also survive ionizing radiation, which we know would be an issue on the Martian surface. So, can life exist on Mars? Based on what we see on Earth, we might possibly see extremophilic microbes. The possibility of Martian life is one of the reasons why we continue to send orbiters, landers, and other space missions to Mars. Humans have been sending orbiters and landers to Mars since the 1960s. The details of these missions and what they discovered over time are excellent examples of how science progresses. Sometimes what we thought was true in earlier experiments will end up not being true at all when we develop better technology and refine our experiments. That is the nature of science. Prior to the space missions, Mars was thought to have life. People saw what appeared to be seasonal changes in the coloration patterns on Mars, and thought that that indicated plant life. Percival Lowell, the founder of Lowell Observatory, promoted the idea that intelligent Martian life created canals on the surface of a dying planet, funneling water from the polar ice caps to the dry regions at the equator. Lowell's ideas were largely debunked, even by his fellow astronomers and scientists. Some believe that imperfections in the lower quality optics may have led to optical illusions resembling lines, as Lowell observed Mars through his telescopes. But though Lowell's views of canals built by intelligent life were found to be false, the idea of life on Mars persisted. The first country to develop a Mars program was the Soviet Union, which began in 1960. But the first successful Mars mission was conducted by NASA in 1964. This mission, Mariner 4, was the first spacecraft to send close-up pictures of the Martian surface. Mariner 4's images revealed a Martian surface that was cratered and barren, disappointing those who grew up with War of the Worlds and Marvin the Martian. Later missions to Mars found that Mariner 4 had photographed a more ancient region. A cratered surface is not typical for most of the Martian areas. Data from Mariner 4 also found that there was no magnetic field or radiation belts. The atmosphere was measured and found to be far thinner than scientists had expected. The next successful mission to Mars was Mariner 6 and 7, which was also launched by NASA in 1969. The two probes were launched within 1 month of each other, but designed to coordinate with each other to study the Martian surface and atmosphere. These two probes photographed approximately 20% of the Martian planet, including the southern polar ice cap. One of the instruments on board, the ultraviolet spectrometer, was built by the Laboratory for Atmospheric and Space Physics at the University of Colorado, Boulder. Mariner 6 and 7 discovered that the Martian atmosphere was mostly carbon dioxide, and the Martian surface did contain trace amounts of water. So by the end of the 1960s, we discovered that Mars had no magnetic field, was mostly dry, the atmosphere was thin, and the older regions of Mars was heavily cratered by meteorites, asteroids, and comet strikes. Intelligent life seemed quite unlikely. The next successful Martian mission occurred in 1971, this time by the Soviet Union. Their mission, called Mars 2, involved an orbiter, a lander, and a rover. The lander mission was ambitious. The lander was equipped with television cameras, a mass spectrometer, and a mechanical scoop designed to search for organic matter. The lander also contained the rover, which was designed to move across the Martian surface on skis while attached to the lander. But only the orbiter succeeded. The lander crashed on the Martian surface, destroying the rover with it. The Mars 2 orbiter was also hampered by the presence of a large dust storm that obscured the surface of Mars. This dust storm, the largest ever observed at the time, sent particles as high as 7 kilometers into the atmosphere. Despite these setbacks, Mars 2 was able to photograph tall mountains and detected the presence of hydrogen and oxygen in the Martian atmosphere. The probe also gathered data on the surface temperature, which ranged from a negative 166 degrees Fahrenheit to 55.4 degrees Fahrenheit. The Mars 2 orbiter also gathered data on the Martian gravity and magnetic fields, something that was missed by Mariner 4. The Mars 2 orbiter remains in orbit around Mars to this day, though communications with the orbiter ended in August 1972. 9 days later, another Soviet mission, Mars 3, entered an orbit around Mars. Mars 3 also consisted of an orbiter, a lander, and a rover. Again, the orbiter was successful. The lander soft-landed on the Martian surface and began to transmit images back to Earth. But contact was lost a little less than 2 minutes after the landing. Since a severe dust storm occurred during the landing, it is thought that the storm damaged the lander's communication system. Mars 3 lander is believed to have been photographed by the Mars Reconnaissance mission in 2013, but the fate of the rover remains unknown. NASA also succeeded in 1971 with their Mariner 9 mission. When it reached orbit over Mars, a severe dust storm was occurring, the same dust storm that is believed to have caused the failure of the Soviet Mars 3 lander mission. NASA scientists delayed imaging for a couple of months until the atmospheric dust had settled. Mariner 9 was extremely successful, sending over 7,300 images back to Earth. The initial goal was to map 70% of the planet, but Mariner 9 managed to map nearly 85% of Mars. These images revealed riverbeds, craters, extinct volcanoes, canyons, weather fronts, fogs, and Mars' two moons, Phobos and Deimos. Mariner 9 continues to orbit Mars to this day, though the mission was shut down in 1972. The next successful mission was in 1973 with the Soviets' Mars 5 mission. Originally designed to last 3 months, it was struck by a micrometeoroid nearly 2 weeks after it began its orbit around Mars. Despite its short mission, Mars 5 returned 48 usable images, and its infrared radiometer revealed a daytime surface temperature that ranged between -47 degrees Fahrenheit and 28.4 degrees Fahrenheit, with nighttime temperatures of -99 degrees Fahrenheit. Mars 5 also discovered a very thin ozone layer and observed clouds in the atmosphere. In 1973, Soviets also succeeded with the Mars 6 and 7 orbiters, though communications with the Mars 6 lander was lost soon after landing, and the Mars 7 lander separated from the orbiter prematurely and never entered the Mars atmosphere. Despite the failures of the landers, the Mars 6 and 7 orbiters discovered water vapor at a higher concentration in the atmosphere than previously detected by the earlier missions. NASA Viking 1 in 1975 was the next successful mission that also included an orbiter and a lander. This mission also included instruments that searched for evidence of Martian life. 4 different methods for detecting organic molecules, thus organic life, were used. Only one test gave a positive result, and scientists still debate whether the positive result was due to living organisms or not. Viking 1 was also used to test for gravitational time dilation, the idea that time will move more slowly when near a source of gravitation and more quickly when it's further from the source of gravitation, a phenomenon predicted by Einstein's theory of general relativity. The results indicated that gravitational time dilations did occur. Viking 2 was another orbiter and lander launched by NASA in 1975. The orbiter was active for 3 years, taking nearly 16,000 images of Mars. This orbiter discovered huge river valleys in numerous areas of Mars and evidence that rain once fell on the Martian surface. The lander landed in a large plain known as the Utopia Planitia near the equator of Mars. The lander conducted soil analyses, finding that the soil near the lander contained a lot of silicon and iron, along with magnesium, aluminum, sulfur, calcium, and titanium. Some of these compounds were magnetic. Viking 2 estimated the soil to be between 3 and 7% magnetic materials. Some of the sulfur and chlorine compounds discovered in the soil samples resembled those that were left after the evaporation of seawater. Water itself was scarce, estimated to be approximately 1%. Viking 2 also had biology experiments, and it yielded the same results as its twin, Viking 1. The consensus after the 1970s was that current life on Mars was unlikely, at least near the Martian equator. NASA did not conduct any Mars missions in the 1980s, and the Soviet Union only succeeded with the Phobos 2 orbiter, which mapped 80% of the Moon's surface. Phobos 2 was the last Mars mission conducted by the Soviet Union, which would fall in 1991. Russia would not have a successful Mars mission until 2016, when it participated in the joint mission with the European Union to launch ExoMars. NASA, however, would have 2 successful missions in the 1990s, the Mars Global Surveyor and the Mars Pathfinder in 1996. The Global Surveyor fully mapped Mars, finding that both hemispheres of the planet were cratered, though the craters were mostly buried in the northern hemisphere. The surveyor found that iron oxide compounds, particularly hematite, were abundant in several regions, indicating that water once flowed in these regions. Dark streaks on the surface was found to be caused by giant dust devils. The surveyor also found that Mars' planetary climate had cooled since the Viking missions in the 1970s, and that the surface was covered with volcanic rock. Most fascinating of all was the discovery of gullies and channels that indicated that water had flowed recently on Mars, possibly at some point between 1999 and 2001. Morning water ice clouds in the lower atmosphere were also found. Pathfinder discovered a pink haze in the sky caused by microparticles consisting of ferric oxide, in other words, rust. The 2000s saw several successful Mars missions. NASA launched Mars Odyssey in 2001, which is still operational, and Spirit and Opportunity in 2003, the Mars Reconnaissance Orbiter in 2005, which also remains operational today, and the Phoenix Lander in 2007. Odyssey and the Phoenix Lander confirmed the presence of water on Mars, including vast water near the surface in the equatorial regions. Spirit discovered that abundant dust is mostly the magnetic magnetite. The Mars Reconnaissance Orbiter made several important discoveries, including that the North Polar ice cap contained approximately the same amount of water as 30% of the Greenland ice sheet. Some of the craters were recently uncovered, revealing water ice underneath that sublimes, which means goes directly from a solid to a gas. The sublimation is due to the thin atmosphere and low atmospheric pressure on Mars. Large chloride deposits and clays were also discovered, further evidence that water once flowed on the Martian surface. Seasonal flows of salty water were also detected, a finding that was later confirmed 4 years later. Phoenix also confirmed the presence of water, but also detected perchlorate, a strong oxidizing agent that is toxic to life as we know it in the soil. This discovery dimmed the hopes of finding active living organisms on Mars, at least in the regions around where the Phoenix landed. But NASA would launch several more landers and rovers to explore the possibility of life, and succeeded with the Mars Science Laboratory in 2011. The Mars Science Laboratory mission included the rover Curiosity. This rover found that ancient Mars had the right chemistry to support living microbes, and organic molecules were detected in several samples that were collected from drilling deep into the soil. Curiosity also discovered seasonal fluctuations in atmospheric methane. Since methane can be produced by living organisms, this seasonal fluctuation in atmospheric methane is particularly exciting to those who hope to find life outside of Earth. Since the success of the Mars Science Laboratory mission, 2 other landers have successfully landed on Mars: InSight in 2018 and Perseverance in February 2021. InSight was designed to study seismic activity on Mars, while Perseverance was designed to not only detect signs of past and or present microbial life on Mars, but also look for habitability for possible manned missions to Mars. I look forward to learning what these missions will discover. I hope you enjoyed today's discussion on Mars. Next month, on April 22nd, I will discuss lagomorphs, pika, rabbits, and hares in honor of Easter. I would like to send a call out to Carl Rosenberg from San Cristobal, New Mexico, who sent me a lovely email regarding the show last month. If you would like to suggest a topic or comment on the show, you may email me at spiderwomankrza@gmail.com. I would like to thank you for listening to what is now my 6th show for KRZA, and I would like to thank the director and manager of KRZA for giving me the opportunity for producing this show. I hope you will tune in next month for Science Views from the Valley.